In this section, we will utilize the SES-DP non-real-time desktop environment shown here to test the inverted pendulum controller and plant distributed process plugins that were auto-generated from MATLAB Simulink models in Part 3 of this video series. The NRT environment allows us to thoroughly test the actual distributed process plugin code that will be used in the hardware-in-the-loop environment with a simulated dynamics plant and support facility. This allows us to take advantage of advanced code coverage, debugging, and analysis tools, such as Rational Purify, that are not available to the user in the embedded real-time environment. The end result is process code that is significantly more reliable, reduced integration time, and ultimately a significant reduction in system costs. Okay, let's go ahead and bring up the non-real-time environment by running this script. And that brings up the SES-DP server node, the facility manager, the SES data monitor, and the scripting command window over here. Now let's start the base processing by pressing the start button from the facility manager. Now you can see the controller and plant SES-DP processes being loaded along with this graphics model over here. Let's go ahead and orient the graphics so it looks a little better. That looks good. Now let's subscribe to the plant dynamics and control system publication data from the SES-DP data monitor. In the facility manager, we've attached some custom Perl scripts to the user configurable buttons. We have a controller on button, 2 tap buttons that impart a small force to the plant dynamics, 2 bump buttons that impart a larger force to the plant dynamics, and a controller off button. Let's go ahead and start the controller by pressing the controller on button. The pendulum controller is now in the swing up mode where it's gradually adding energy to the system. And it's now transitioned to the hold mode. Now it's walking the pendulum over to the 0 radian location. And now the pendulum's vertical and holding. Now we can use the buttons that I described previously to tap the pendulum or bump the pendulum. So let's go ahead and tap it in the positive direction. As you can see, the controller keeps the pendulum upright during that operation. We'll do the same thing with the negative direction. Now let's go ahead and bump the pendulum. That imparts a larger force, but the controller can handle that as well. We'll bump it in the negative direction now. And the controller walks the pendulum back to the 0 radian position. Okay, let's interact with the distributed processes that are running on this server node by bringing up the SES distributed process monitor. As you can see, this distributed process monitor is communicating with the distributed process server running on this machine. And there are the 4 distributed processes that are currently loaded and running on this system. Here's the pendulum controller, which was generated from MATLAB Simulink, the pendulum dynamics, which is running the simulation of our plant hardware, the subscription archiver, which is responsible for archiving all of the plant and controller process publication data to disk, and the Pendulum 3D animated graphics application. I'm going to go ahead and take a look at the pendulum controller distributed process. I can do that by right-clicking on this and opening up this control window. As you can see, all of the commands that are available for the pendulum controller distributed process are listed here. We have the standard commands such as initialize, validate, start, stop, pause, continue, get properties, and get state, as well as the process specific commands such as query parameters and update parameters. The query parameters and update parameters commands are automatically put in by the code generator, and they allow the user to view and update the MATLAB generated Simulink parameters that are contained within the MATLAB Simulink model. Let's go ahead and take a look at the current parameter settings by sending the query parameters command to the process on the SES-DP server. Now we have all of the MATLAB Simulink parameters that are contained within the controller model. As you can see, there are things like controller gains, desired set positions, saturation values, etc. Now let's go ahead and modify some of these and see what happens with our control system, which actually is active right now and running on the distributed process server on this node. We'll do that by bringing up the controller's update parameters command. Now what we can do is we can go in and we can change some of these MATLAB parameters on the fly, and that'll cause our system to react. All right, let's first change the desired swing arm angle. Right now it's at 0 radians. I'm going to set that to 1 radian. As you can see, the model walks over to the 1 radian location. Set that to -1 radian. And we'll set it back to 0. All right, now let's play with the stability of the controller. I want to make the control system oscillate. I can do that by changing the control gains in the system. So I'm going to go ahead and change the swing arm rate control gain to 2. And I'm going to change the swing arm angle gain to 8. Let's go ahead and set that. Now let's tap the pendulum. As you can see, the system is now oscillating. We can remove this oscillation by setting the swing arm gain parameters back to the proper values of 4.11, 3.87, and you'll see the controller walk right back into the 0 location. We can also do some interesting things by changing the pendulum hold angle. The pendulum hold angle is currently set to pi. Let's set that to 3.1 radians. Let's go ahead and send that. Because the set point is now programmed to just under the vertical position, the swing arm is forced to propagate in the clockwise direction. You'll notice a slight disturbance that results in this case as the swing arm passes through pi radians. This is because the swing arm error signal changes sign at this point. To remove this disturbance from the system, we can set the swing arm position gain to 0. The system now transitions through this position without issue. Now let's set the pendulum hold angle to 3.2 radians. Because the set point is now programmed to just over the vertical position, the swing arm is forced to propagate in the counterclockwise direction. And if we set the pendulum hold angle back to pi, you'll notice it'll just hold out here now because now the rates have taken over and there is no position gain. Let's go ahead and put our position gain back in, 3.87, and you notice the control system will walk the angle right back in as desired. All right, so that gives you the idea. Basically, because we've converted the MATLAB model to a distributed process, we can dynamically change any of these parameters on the fly while the system runs in hard real time. In this case, our controller plugin is driving a dynamic simulation of the pendulum hardware. However, the same procedure can be used when we move the controller plugin into the real-time environment and run it closed loop with the actual pendulum hardware. This is shown in Part 5 of this video series. Alright, I'm going to go ahead and turn the controller off. And if I tap it, it'll knock it over immediately. We can turn the controller back on. We'll let it swing up one more time. And I'll go ahead and shut it off again. As expected with the controller off, the pendulum falls and its motion gradually decays. Now to unload all the active distributed process objects that are a part of this configuration, all I need to do is press the stop button. You'll notice everything goes away. And now we're back to the point where all the distributed processes are unloaded on this particular node.